We have about a month left into the semester before the final exams, and that also maybe not the entire month because we have Diwali break coming up. But I think because of the Diwali break, we will probably miss only one lecture next Monday. I think next Wednesday is when we will start the lectures again. The semester will start next Wednesday. I had told you that today's lecture might be taken by Professor Aditya Tatu on this graph signal processing topic, but he is not available today because of some family reasons. So he has told me that he will be taking this lecture next Wednesday. So next Wednesday at 10 is when his lecture is scheduled. And then we have one more lecture from ISRO lined up. That will happen sometime in the first week of December. Okay. So this is, today I wanted to mainly review one paper on sphere decoding. And this is the last topic that I want to cover as a part of this generalized modulation, demodulation topic. In the lab that I have given you, I have not included this topic of sphere decoding, but it actually is a kind of a natural extension to those 6 algorithms that you are studying as part of lab 4. The 3 of those algorithms are the linear algorithms, SUMF, the zero forcing decorrelating detector, MMSE. And the other 3 algorithms are non-linear, the SIC, the multi-stage, and the decision feedback. In contrast to that, this algorithm that we are going to look at now, the sphere decoding algorithm, I wouldn't call it, I don't think it falls into any of these 2 categories. It is not definitely linear algorithm, and it is also not, I wouldn't say it is, it has any relation to SIC or multi-stage or decision feedback IC. I would probably consider it more as a dynamic programming type of algorithm. It has some similarity to Viterbi decoding, but really not even Viterbi decoding as such. It kind of, I would say it is more of an enumeration algorithm. You just consider all the possibilities of the transmitted symbols, and then you intelligently prune down your search. Okay, so this is almost like a brute force algorithm, which, if I want to give you kind of a very high level preview in a nutshell, this is what the sphere decoding algorithm is. Okay, so we have said that the optimal receiver is the one which considers this reception model that we have seen earlier, the reception model that we have seen here in this equation. And the optimal receiver, as we know, the maximum likelihood receiver, selects that value of S for which the distance between R and the corresponding H times S hat is minimized. That is what we mean by the maximum likelihood detector. It minimizes the Euclidean distance. Now, you may have noticed that that distance minimization was the approach that we took in least squares algorithm that we studied last time. The least squares algorithm, if you recall, especially when we consider this calculus-based approach, it actually performs some type of distance minimization. We defined the mean squared error in this manner, but this definition of the cost function is nothing but it is calculating the distance between the received vector r and the estimated vector r hat. So that this is the distance profile, and we take that estimate of s, which minimizes the distance. That we also saw in linear algebraic context. This is r, and this green circle is our r hat, and we selected r hat, which minimizes the distance, the Euclidean distance denoted by the square root of the norm of this vector e. So the distance minimization is what we have done already in this linear methods, the least squares method. Even in MMSE, as you may recall from the last lecture, we do some type of distance minimization because we said that our MMSE estimate S hat is such that it minimizes this mean squared error. But if you look at the definition of mean squared error, it is nothing but the expected value of the squared distances. And so in that sense, if I go back to this equation, one may say that the least squares and the MMSE already perform the Euclidean distance minimization. And so are they not the maximum likelihood methods? And the answer is that they are not maximum likelihood methods because of a very crucial aspect of this equation 11. And that aspect is that this S, the vector S, is not continuous. It is not an analog vector S. It is discretized. If all the transmitters are BPSK modulated, then S is only taking 1 and -1, just two values. For QPSK, individual elements of S take 4 values and so on. They don't take analog values. They don't take infinite set of values. If they did, then yes, one can argue that least squares or MMSE actually do perform the distance minimization. But here now, in the case of least squares or MMSE, we get an estimate of S, which is real valued number. And then we project that real valued number onto one of the possible discrete values, 2 and in the case of BPSK. And it is that projection which messes up the maximum likelihood aspect of the detector. And so that is where the sphere decoding comes into play. The objective of the sphere decoding is that we will not do that projection in an ad hoc manner. That is what is done in least squares or MMSE, decorrelator or MMSE. We do the Euclidean distance minimization, but then the answer that we get is a real valued answer, and we don't know what to do with it. And so we take the simple approach, which is to project it, which is to convert it into the one of 2 BPSK symbols. And that we do just by taking the, for example, in case of BPSK, we just take the sign of that real valued number. Fear decoding says that I will actually take this vector S and consider all possible realizations of S. So let us say that this capital K is equal to 2. There are only 2 users. In that case, this vector S can have how many possibilities? Anyone? In case of BPSK, what are the possible values of vector S when capital K is equal to 2?
Four possibilities.
4 possibilities, correct. 1, 1, 1 minus 1, minus 1, 1, and 1 minus 1, minus 1. So 4 possibilities are not too many. Remember, in all of these detection techniques, we assume that H is known, matrix H is known. So I can take each one of those 4 possibilities, multiply it by H, and that will become R hat, my estimated R. And then I will just take the Euclidean distance between R and R hat. So basically I'll get 4 distances, and then I'll pick the one particular S vector for which that distance becomes for which the distance is the smallest of these 4. Does it make sense?
Yes, sir.
So
Yes.
this is something that you can actually experiment with as a part of your lab. Because in this lab, we are considering a small number of users. Basically, capital K is not very large. What I just described, it is very simple thing for you to implement in MATLAB. It will be just few lines of code. You have to, when capital K is equal to 2, you have to enumerate basically all these 4 possible vectors S. For each of those vectors S, you will take H times S. That will give you R hat. Then you calculate the Euclidean distance between R and R hat, and then take minimum of those distances. And that becomes your estimated S. That is the maximum likelihood estimate. And you should see that it outperforms all of these 6 techniques that you are implementing, these 6 algorithms. Now, the reason I say that it is possible for you to do it in the lab is because capital K values are small. I think we go only up to 8 or so. So it is still feasible to do this. When K is equal to 8, instead of 4, you will have 2 to the power 8 possible vectors S, 256. So MATLAB can cope up with 256 different vectors S. Memory consumption will increase a little bit, but not a whole lot. Computations also will increase. H times S will have to be performed 256 times, but it is doable within MATLAB. The problem comes when capital K starts becoming large. If K is not 8, but if it is 20, then now we are looking at, like, we are stretching MATLAB to its limits. If k becomes 30, then MATLAB would give up. To do the enumeration, the brute force exhaustive minimization of distances for 2 to the power 30 possibilities, it is too much. And 30 is not even that large. If k becomes 100, meaning that there are 100 simultaneous users, then all bets are off. And in 5G systems, the technology that is being proposed is called massive MIMO, where capital K denotes the number of transmit antennas, or it could be number of receive antennas. And in massive MIMO, there are a large number of antennas. In 4G, MIMO systems typically have maybe 4 antennas, or at the most 8 antennas. In 5G, in massive MIMO, there may be 100 antennas or 200 antennas. And so now when k is 100, if you have to do this enumeration for 2 to the power 100, that is not possible. It is not possible today, and it's probably not going to be possible ever in the future. Simply because 2 to the power 100 is a very large number. And so that is where this sphere decoding comes into play. I want to talk about this sphere decoding because it is a smart way to solve this problem. We have just concluded that as capital K becomes large, this brute force distance minimization becomes computationally impractical. And the sphere decoding is a smart way of solving this computational problem. Now, apart from anything else, what I would like you to focus on is how a difficult looking problem, how some ingenious people, some clever people came up with a smart solution to it. Okay, so a lot of people would probably look at this problem and say, forget about it. This is not doable. They would just walk away. And the sphere decoding and several of its variations that we are going to look at now, apart from anything else, the way they impress me is by showing that it's this smartness of the human brain which is at play here. So that is probably the main takeaway that I came up with when I understood the sphere decoding methodology. Okay, fine. So we are now going to look at this paper by Larsson that talks about sphere decoding method. And by the way, here the problem statement is exactly same as our generalized model. Y is equal to h times s plus e. There are some notation differences that I have tried to mention here. Somewhat different, but not very different. R that the vector that we have called R, the vector of received, signal is denoted as Y. Okay, so that is the main one of the main notational differences. But otherwise, you see H and S are similar. E is the noise vector, and this vector S has elements S of k which belong to a finite alphabet, which is to say that they belong to the constellation diagrams, either QPSK or Emery PSK, Emery Quam, etc. Okay. In sphere decoding, there is one assumption that all the quantities are real valued. And this is some detail that we probably don't need to get into too much. Only thing that I would say is that it's not a big deal. I mean, typically we consider QPSK or QAM symbols as complex valued, but we can also consider them as a pair of real valued numbers. So if I consider an n-dimensional space of complex numbers, it actually is equivalent to a 2 times n-dimensional space of real numbers. And so for mathematical derivations, although the elements of S, this vector S, are considered real valued, it doesn't mean that this method applies, for example, only to BPSK or pulse amplitude modulation. It applies to all the different modulation schemes that we have learned, except that instead of considering them as complex valued entities, we would have to turn them into real valued numbers. An assumption is also that m is greater than or equal to n, where m is the number of rows and n is the number of columns. So n defines the number of simultaneous users, which we have called capital K in our notations. And m is equivalent to capital N in our notations. Okay, so this is the statement of the problem, the maximum likelihood problem, that we want to detect S so that the Euclidean distance y minus hs, the norm of that difference, is minimized. And so the solution is a finite alphabet constrained least squares problem. And the least squares method that we have studied is not constrained by this finite alphabet aspect of this vector S. And so if we want to do this least squares solution with this finite alphabet constraint, then we run into this NP-hard computational difficulty, which is what we just talked about, that as S becomes bigger and bigger vector, then the number of possible vectors that we have to consider in this distance minimization becomes just exponential. It is not computationally feasible. If this finite alphabet constraint was not present, then that will just be classical least square segregation, which is what we have already seen, the decorrelating detector. Okay, so this first two columns of this paper we are very much familiar with. We fully understand based on our earlier discussions in this class. Okay, now for sphere decoding, the author says that I will first do QL decomposition of H. Okay, so let us see what QL decomposition is. QL decomposition is similar to QR decomposition, which we may or may not have talked about explicitly, but it is nothing but the Gram-Schmidt orthogonalization of matrix H that we certainly have studied in CT516. Do you remember this Gram-Schmidt orthogonalization that we did earlier?
Yes, sir.
Right.
Yes, sir.
The way Gram-Schmidt works is we take the first column of H and we normalize that. And that becomes the first column of Q. Then we want to derive the next column of Q, which is orthogonal to the first column. And to get that column, the second column of Q, we take second column of H, and from that we subtract the projection of the second column of H onto the first column of Q. And that we keep on doing for all the other columns of Q. Okay, so the end will be the end output. The final output will be a Q matrix, which will have same number of columns as the columns, the number of columns of H. And then there will be another matrix which will be a lower triangular matrix. And so with that, we would have decomposed H into Q times L. Q is the matrix of orthonormal columns, and so Q Hermitian Q is always equal to identity matrix. And L has a size of K cross K. And if we start from the first column of K and go to the last, first column of Q and go to the last column of Q, if you go first to the last, then we may have L as an upper triangular matrix. And then it is called QR decomposition of H. On the other hand, if we go from the last column of Q and come to the first column of Q, then we will have a lower triangular L matrix. And then in that case, it is called QL decomposition. That is just a matter of practical implementation. It has no significance other than that. So QL or QR are equivalent. Because the paper by Larsson considers QL decomposition of H, we'll just continue with QL. So with H represented as Q times L, the correlation matrix R becomes nothing but L transpose L. Because we have just now said that Q transpose Q is identity. So now, this is sort of like the Koleskis method that we have already studied, which says that instead of inverting R, which is what decorrelating detector does, I will simplify R as this product of triangular matrices. And so now this vector z, which is, remember, the vector of sufficient statistics. Am I audible?
Yes, sir.
Yes, sir.
Okay. So vector z is the vector of sufficient statistics. What is the other way to interpret vector z, which is H transpose Y?
Match filter, single user match filter.
Yes. So z is the SUMF, which we have written earlier as correlation matrix times vector S plus some transformed vector of noise, which we are going to call it U. But now I'm going to take this H and write it as L times Q. I mean, H transpose becomes L transpose times Q transpose. And this R is already L transpose L. So do you see how I got the second line from the first line? Komal?
Hello.
Yeah. Do you see how we derived the second line from the first line? First line, as we just now said, is nothing but the SUMF formulation that we have seen earlier. The second line is the new one. Did you see how we can derive this second line?
So last week we have defined that thing.
No, the second line is new. This is the first time we are talking
Oh,
about.
this okay. This time.
Do you see how we got this second line?
So R will be equal to L Hermitian L
Yes.
and into S
Yeah.
plus
So R times S is same as L Hermitian L times S.
yes
And this sigma H Hermitian N is what I'm calling U.
U. Okay.
What about this here? Do you see how I got that?
So I'm looking into it.
H is equal to Q into L, so H Hermitian is
Yes. So Divya gave the
L
answer.
Hermitian into Q Hermitian. Yeah, H Hermitian.
So H Hermitian Y is L times Q times Y,
Q.
right?
Mm-hmm.
Okay. So now that we can write it like this, the next step is okay. So instead of giving you the next step, I will ask you what would be the next step now? Remember, we are doing this as of now to try and simplify the decorrelating detector so we don't have to perform explicit matrix inverse. And if we can cast the problem in terms of either lower triangular or upper triangular matrices, then we don't have to perform matrix inverse, because if let's say X is equal to A times B plus some noise, But if we know that A is a lower triangular matrix, then I don't have to invert A. I just go from the first row of A to the second, to the third, and so on. We do what is known as either forward substitutions or backward substitutions. How do I get to that desired form given this second line, which is I've highlighted? See, right now my unknown variable s, which is what I want to determine, I can't write it as a product of lower triangular matrix times that unknown vector, because L Hermitian L is not lower triangular, it is this R matrix. So this highlighted line is not sufficient still. I have to do one more mathematical operation on this highlighted line so that it turns into a form which I want. And I'm asking you, what is that operation that I will have to perform?
3 multiplied by L Hermitian inverse.
Exactly. Good, Divya. That is exactly the answer. We multiply both the sides of this equation by inverse of L transpose. Okay, and so once we do that, we get this last line where y tilde is q transpose y. Right? So what is q transpose y? It is nothing but the projection of the SUMF, it is the projection of the received vector y So this SUMF is the projection of received vector y onto columns of H. So individual columns of H are the match filters for the individual users. And so that is why this H transpose Y gives us the vector of SUMF output. So in this QR method, instead of projecting Y onto columns of H, we project Y onto columns of Q instead. And columns of Q are orthonormal. So basically, in some sense, we are to an orthonormal basis. And the result is not SUMF anymore, but it is so sort of like SUMF, as if these individual vectors are orthonormal. So that is Y tilde. And that Y tilde, we can mathematically write it as the product of the unknown variable vector S with a lower triangular matrix L. Right? So, I mean, we did some math here, but the bottom line is that instead of projecting Y onto the columns of H, we are projecting Y onto columns of Q. That is all. We have to first determine what Q matrix is, and for that we have to do QR decomposition. But once we do that, then this part here is computationally it is same as SUMF. We are just doing projections, a bunch of projections. And then the resultant equation that we get is sort of like the SUMF equation only. The difference is that R, which is generally not a triangular matrix, it kind of magically became a triangular matrix. And so now all that I need to do is do the back substitutions, and I'll get the estimated S without needing to do matrix inverse. Okay, so that is the idea behind solving the least squares using QR decomposition. If you recall, in the Kolesky's method also we did something similar. We turned the problem into a triangular problem, and then we did the back substitutions. But unlike the Kolesky's method, here the way we get the triangularization is different. We do it by Gram-Schmidt or orthogonalization of matrix H. Okay, so that is the main idea, that the problem is turned into y tilde is equal to L times S plus V, where V is the noise vector. But so far we are still talking about the decorrelating detector, and we have only talked about how to efficiently implement decorrelating detector so that we don't have to do matrix inverse. The sphere decoding now says that I'm going to take this lower triangular formulation of the problem, and I'm going to do distance minimization on that. And the argument is that performing the distance minimization on, well, I'll just go to the paper now. Performing distance minimization on y minus h times s. The argument is that it is same as performing distance minimization of y tilde minus ls, where L is the lower triangular and y tilde is the Q transpose Y. Y tilde is same as this Y tilde, which we have seen here. And L is also same. So the argument is that the minimization problem in equation 2 is same as minimization problem in equation 3. Why it is the same is what we kind of saw just now, using this few simple derivations. Okay, so now I'm going to give you a math challenge. Okay, so this math challenge does not require any prerequisites. It's like purely coming out of your linear algebra class. We kind of already saw in an easy way. This is kind of a simple way, but maybe it is not mathematically rigorous way. Through this argument, which I believe you understood, at least Divya understood. Actually, Divya gave me this equation here even before I showed it on the screen. And so I believe most of you have understood this derivation. And so in light of this derivation, we are kind of already willing to say that minimizing y minus hs, equation 2, is same as equation 3. minimizing y tilde minus ls. The math challenge that I want to give you is this equation here, which I highlighted. The author is saying that y minus hs norm squared, minimizing y minus hs norm squared, why it is same as y tilde minus ls norm squared minimization. The author is proving that by this highlighted equation. And this is the challenge that I'm giving you. I am not going to get into that. I'm asking you that you derive this unnumbered equation between equation 2 and equation 3. It will be challenge, okay? It's not trivial. See, this paper is very nicely written. It is very easy to understand, except one part, which is this equation here. The author has not given any explanation of how y minus hs norm squared, he can write it like this. And then he has not explained if he can write it like this, then from that how he can write it like this. And the reason why the author has not given any explanation about that is because he's kind of reading between the lines. He's saying that this is just your linear algebra problem. I don't need to solve it for you. You can do it yourself. You don't need any signal processing or communication background for that. So this is the kind of interesting part. It took me some time, actually. I will say that it took me some time to do this. I didn't need to do it because I knew this shortcut, which we just went over. So because of this shortcut, I was already convinced. I mean, I already knew that equation 2 and equation 3 are same. And the way I could prove that they are the same is by this derivation here, which is a much simpler derivation. But this is not mathematically rigorous, because here I'm just saying that z is equal to y tilde and r is equal to l. And therefore, z minus rs is same as y tilde minus, z y minus hs should be same as y tilde minus ls. But over here, it is explicitly shown that y minus hs norm squared is same as y tilde minus ls norm squared. So, but this derivation method is very different from the simpler way that we came to equation 3. I'll give you a hint about how to go from this left-hand side to the right-hand side of this first line. What the author is doing is, he is calculating the length of this error vector, y minus hs. Because the squared norm of y minus hs is nothing but, as you know, the length of this vector y minus hs, which we can call the error vector. Now, the hint I will give you is that if I want to measure the squared length of a vector, I can either measure it directly by taking the squared norm, or I can project that vector, error vector y minus hs, onto two perpendicular axes. And then I apply Pythagoras theorem, right? If I can project this vector E y minus hs onto two perpendicular axes, and then I apply Pythagoras theorem, then y minus hs, the vector E, becomes the hypotenuse. So the square root of the hypotenuse is equal to the square root of the two legs of that right angled triangle. And so the hint that I'm giving you is to show that this error vector is getting projected along two perpendicular directions by this. Once you show that, then you are done with the first line. Then you have to go to the next line and show how did this term here became this term. And then you have to show how did this term became this term. And that is purely algebraic manipulations. So this is a way that you can derive this unnumbered equation. Okay. So let us take a break now, and we will then look at sphere decoding in the next half an hour or so. I'll be back in just a few moments. Okay, so now, as this equation 3 says, we have converted the Euclidean distance minimization problem to an alternate form where the unknown variable, a vector s, is getting multiplied by not this matrix H, the MIMO matrix H, which will have non-zero values on all its elements. Instead, it is getting multiplied by matrix L, where L is a lower triangular matrix. And the reason why this is beneficial is because of the lower triangular nature of L, that distance minimization problem can be written as this equation here, where the first term is dependent only on S1. The second term is dependent on S1 and S2. And then the last term is dependent on all of the S parameters. And this F functions are nothing but the Euclidean distances of individual element of Y minus the product of vector S with the corresponding row of matrix L. So let us see that by means of an example. Let us assume that n is equal to 3. And because L is lower triangular, y tilde minus L times S is going to be the vector which is shown here. y tilde 1 minus the first element of L matrix times S1. And y tilde 2 minus L21 S1 minus L22 S2. And then similarly the third row of this vector. Who agrees with this equation that I have written? Anudeep? Are you fine with this equation? It looks like Anudeep is not here today. Pavesh?
Yes, sir.
Does it make sense? Kishan, what about you?
Yes, sir. It kind of follows from the lower triangular property.
Right. Follows from the lower triangular form of L matrix. So now if I want to take the squared norm, obviously it is the square of the individual elements of this vector. And so I can write it like this. And so you will see that the first term here is a function of only S1. The only unknown in the first term is S1. That is what Larsson is calling F1 of S1. The second term is a function of S1 and S2. That is what he is calling F2. The third term has all the three symbols. And that is F3 of S1, S2, S3. Okay, so with that, now we will jump into Larsson's paper. And we will see the main idea behind sphere decoding. So obviously, a simple way, which is a valid way of solving this equation 4, is to enumerate all possible values of S and then take the one which is the smallest, it gives the smallest value of this summation. But that is this back to our brute force technique, which is inefficient because there are just far too many combinations of this S vector that we will have to examine, especially as the number of users or number of antennas goes up. Okay, so before we get into the sphere decoding, let us look at his description of the zero forcing detector, which is our decorrelating detector. And you see that it is written as L inverse Y tilde. L inverse Y tilde is exactly how we did it here. We get Y tilde is equal to L times S plus V. Then to get S, we will just do L inverse Y tilde. So that is going to be our decorrelating detector. Except that he says that L inverse doesn't need to be explicitly computed because we can do this back substitution or the Gaussian elimination. Okay, so this is again same as what we have examined. And then over here, the author talks about the disadvantage of this decorrelating detector, which is that if the columns of H are making small angles with respect to each other, which is to say that H is not well conditioned, then there will be noise enhancement. And then the author says that instead of doing least squares, we can do MMSE, which is also an algorithm that you are simulating in lab 4. And the author is saying that yes, this will improve the performance a little bit, but maybe not too much. So the author gives maybe half a column to the zero forcing and MMSE. But the main focus of the author is to give an example of this equation, how it will look like. Remember, the first term is dependent only on S1. The second is dependent on S1 and S2. The last one is dependent on all of the S values. And so the author says that I can consider the evaluation of this the Euclidean distance in this manner by this binary tree, where the first branch of binary tree is dependent only on S1 and its values are determined by these values of function f1 when s is -1 and s is +1, the BPSK case. And so the author says that maybe for some specific realization of this f functions, I got two values, 1 and 5. Now I will go to the evaluation of the next function, which is f2. And then f2, remember, is dependent on s1 and s2. And so there will be four possibilities: -1, -1, -1 +1, +1 -1, and +1 +1. And the values of f2 for the first possibility is -1 -1 is 2. f1 was 1, and so the summation becomes 3. The second possibility is -1 +1, and for that f2 turns out to be 1 in this example. And so the net value becomes 1 + 1, which is 2. And then same way, f2 for 1 - 1 is 2 and 1 1 is 3. And so these two nodes are having values of 7 and 8. And then the third level is considered, for which now there are f3 has total of 8 values: 4, 1, 3, 4, 3, 1, 1, 9. These are the f3 values. And f3 has 8 possibilities, because now remember f3 will depend on s1, s2, and s3. And s1, s2, s3 can be 8 possibilities. And so for each of those 8 possibilities, f3 values are written here. And they have to be added to the previous summation, which is f1 plus f2. So 3 plus 4 becomes 7, 3 plus 1 becomes 4, 2 plus 3 becomes 5, and so on. And so we got this total of 8 possibilities, which we have enumerated. And so the final answer is -1, -1, 1, because the corresponding distance 4 is minimum of all of them. Is this fine? Who has not spoken yet? Nidhi, is this fine with you?
Yes, sir.
Okay. Arushi, what do you think?
Yes, sir, fine. Understood.
Okay, good. But so far here we are not simplifying anything. We are still calculating all these 8 distances. Maybe we are calculating it in a smart way, but the basic problem still remains that if we have to do it for 8, it is doable. But if you have to do it for 2 to the power 20, then this becomes too much. This tree will become too big. Okay. So then the author says that the way to, okay, well, before going to sphere decoding, the author talks about the decision feedback interference cancellation, which we already have studied. Remember, in decision feedback, we actually converted the problem to this type of problem, a lower triangular problem. And then we were doing successive interference cancellation on this lower triangular problem. Remember that? If you already implemented decision feedback, then you would be very much familiar with that. But otherwise, that algorithm is repeated here. In that lower triangular version, we first detect S1 hat as simply Y1 divided by L11. Then, using that estimate of S, we detect S2, which is Y2 tilde minus S1 hat L21 divided by L22, and so on. And so, this is the decision feedback algorithm, which the author says that we can understand from this decision tree perspective. We can say that when we are deciding S of k, it is as if we assume that the prior values of S are already known. And then we take that value of S of k, which corresponds to the smallest branch metric. Okay, so let us take an example of that. This is the same decision tree as before, but here we are going to go down the decision tree by assuming that we have already correctly identified the previous symbol. So from the root, we go to the first level, and there obviously this S1 equal to -1 wins, right? Because compared to +1, -1 gives me a lower metric. And so I have decided that S1 is -1. And so now I go to the next level, but that time, because I have already decided that S1 is -1, I don't need to consider this entire subtree at all. It is gone. And here I'm going to say that if S1 is -1, then what is my best estimate of S2? Obviously, I'm going to take this as my best estimate. So I'll get S2 as equal to +1. And so I'm going to go to this node here. And then I'm going to say that, okay, now I will let you decide whose turn it is. Joel, what will the decision feedback algorithm do after it has decided that S1 is equal to -1 and S2 is equal to +1? What will it do now?
Sir, it will calculate S3 based on S1 and S2.
So what will be the answer?
So like so L times S1, L corresponding to like S1 times S1 plus L corresponding to S2 times S2.
No. I'm saying, look at, I'm showing you this decision tree. In this decision tree, the decision feedback method has decided that S1 is equal to -1. Why? Why did it decide that S1 is equal to -1?
Because of the like shorter distance.
Yeah, because F1 for -1 is smaller. -1 is 1 and +1 is 5. Which is to say that if I map this y tilde 1 on real valued axis, that y tilde 1 will be much closer to -1. Maybe it will be -0.8. And so its distance from S1 is much smaller than the distance from +1, which is 5.
Okay.
Basically, if I do sine of y tilde 1, it is going to be a minus sign because it's closer to -1. The closeness to -1 is indicated by F1. And so it selected S1 as -1. Why did it select S2 as +1 now?
Because F2 of -1, 1, like it, the point will be closer to F2 of like -1, 1.
Yeah, so the decision feedback says that my estimate of S1, which is now -1, I'm going to pretend that it is the correct estimate. And so I'm going to subtract that estimate from Y2 after multiplying S1 hat with L21. And then that result, how far it is from actual Y2, is given by F2 values. And those F2 values are smaller for the case when S2 is +1, right? F2 value is only 1 in that case. Otherwise, F2 is 2. And so in the second iteration of this decision feedback, the algorithm is going to say that S2 is +1. In the third iteration, it is going to do this computation. Y3 will be so L values with S1 and L value product of L values with S2 will be summed, and that sum will be subtracted from Y tilde 3. In the context of this diagram, the result will be what?
S3 will be -1.
S3 will be -1. So the algorithm will go like this. So you see that it arrived at an answer very, very efficiently. In the first step, it got rid of half of the subtree. In the second step, it got rid of another half of the subtree. It is like really pruning the subtrees in the fastest possible manner. But you see that it arrived at an answer which is wrong. Not that wrong. Compared to 4, the value is 5. But the bits are wrong. -1, -1, 1 became -1, 1, -1. 2 out of 3 bits became wrong. And the problem of error propagation in this successive interference cancellation or its alternate form, which is this precision feedback, becomes very clear here. See, the first decision it made is correct. It is going in the right direction. If suppose the first decision itself was wrong, then it got lost right away. So at least first decision it made correct. But the second decision it made wrong. It went in the wrong manner. It should have taken this path. But instead of that, it took this path. Who can explain to me why it should have taken this path?
So because the
So
eventual
because the
would have been
eventual
the eventual distance.
Yeah, the smallest distance is 4, and to get to 4, it should have taken this path. Then why did decision feedback take this path?
So because it's like some heuristic algorithm which is evaluating the some function at every step, and it is going in a certain.
Yeah, so why it took this path instead of this?
Because F2 is smaller.
Exactly. F2 is smaller, and so decision feedback will be forced to take this path, and that is where it made error. And from that point onward, everything that it does is going to be wrong. That is called the error propagation. Once you make a mistake at a particular level, all of your subsequent calculations are going to be likely to be wrong. So that is what is shown here. This is the decision feedback. Okay. Now, in light of that, we are now ready to look at sphere decoding. The idea behind sphere decoding is to say that I'm going to look at the leaf nodes of this decision tree. And by the way, these leaf nodes are basically all possible combinations of this S vector. If S is BPSK and there are a total of capital K users, we have said that it will be 2 to the power K. If there are 100 antennas and if each antenna is simultaneously transmitting a BPSK symbol, we will have to look at 2 to the power 100 possibilities for this distance minimization. And those 2 to the power 100 possibilities are these leaf nodes of this binary tree. The sphere decoding says that I'm not going to look at all of those leaf nodes because those are far too many. I'm going to just limit my search to the nodes which are at radius of 6 and less. Okay, so obviously, if you think of the received vector y as a point in this multidimensional space, and if I create a sphere around it with certain radius r, in this case it is equal to 6, and if there are, let's say, few points within that sphere, then obviously I need to do this distance evaluation only for those points and no more. Why? Because if there is a point which is inside that sphere, then it is going to be closer to all the points. That point is going to be closer to the vector y compared to all the points which are outside of the sphere. Does it make sense?
Yes, sir.
If I can trap, let's say even one point within the sphere, then I can be sure, there is a guarantee that that point, remember the sphere is centered at the received vector. Center of the sphere is the received vector. And now within that sphere, if I can trap even one point, let us say, then I can be sure that that point which is trapped inside the sphere is going to be closer to the received vector compared to all the points which are outside of the sphere. And so I don't need to do the evaluation for any point which doesn't fall inside the sphere. That is the idea behind sphere decoding. And so in this case, this example takes radius r equal to 6. And so it will say that, oh, by the way, in this decision tree, one property is that of this metric values is that they keep on increasing as you go down the branches. Because these f values are never negative. Remember, these f values we are defining as squares. Squares cannot be negative numbers. At the most, they can be 0. So you will see that as I go down any particular route of this tree, the numbers keep on increasing, 1, 2, 5, or 5, 7, 10. And so the idea behind sphere decoding is that I will set some radius and I will keep on examining all the branches of this binary tree. But if I reach a branch whose end metric becomes more than r, then I can get rid of all the subtrees below that particular node. Because all the nodes below that are going to have their metric which is going to be greater than 6. So the example is shown here. The algorithm starts and at the first level it computes 1 and 5. They both are less than 6. So it cannot stop counting. Goes to the next level. Here it gets 3 and 2. So it still has to keep on searching along this branch. But look here what happens. From 5 it went to 7 and 8. As soon as it reached 7 and 8, it says that I am not going to bother about all the nodes that lie below this 2 nodes, because they are going to be outside of my sphere. And so in one fell swoop, it got rid of half of the nodes. And then it did the minimization over the remaining half, and it got the right answer. Does this make sense?
Yes, sir.
I have one doubt.
Yes.
Sir, 4 and 5 both will be less than 6. So how will it decide which one to take? So it will decide that because 4 is less than 5, so it will be nearer to the point.
4 and 5 both are less than 6. So what is your question?
So then the algorithm will take the least of them, 4 and 5.
Yeah. I mean, it got 4 values, 7, 4, 5, and 6. These are the distance values, remember. And we want to do the distance minimization, and so it will take 4.
Okay.
Suppose capital K was not 3, but suppose it was 4. Then who can tell me what will happen in the next iteration? Suppose there was one more level of this tree. Pavesh?
So in the next level also it will go for the minimum version, right? It's already on 4. So
No, I'm saying that if there was one more level, then this sphere decoding with r equal to 6, what will it do?
Sir, it will go down both the nodes 4 and 5.
It will go down?
On both the nodes 4 and 5.
Why not 6? Why will it not go down this 6, children of 6? And why not 7?
For 7, so it will not go because 7 will be greater than the radius r.
summation is greater than radius r.
Exactly. So it will go down the children of 4, 5, and 6. And it will not go down 7. Maybe what Arushi is saying is also possible, that the algorithm says that it has to be less than the radius. Then even 6 will be ruled out. So it will go down only 4 and 5. Okay, so this is called sphere decoding without pruning. So you see that here we already have kind of made use of several smart ideas. This is a lot of brainy stuff, I would say. First part is this here. Converting this problem into lower triangular problem using this equation. That itself is a novelty. And then saying that once I convert it into the lower triangular form, I can develop this type of decision tree. And then saying that I will examine this decision tree in a smart manner by setting up a radius so that I can delete a lot of the decision tree. I don't have to examine all the leaf nodes. There is one more smarter version of this sphere decoding without pruning, which obviously you will guess that it will be called sphere decoding with pruning because it is smarter. And what this algorithm says with pruning is that I don't know how to set radius of the sphere. But actually I'll be looking at the data, and based on that only I will be continuously adapting the radius. Here the radius is fixed, it is 6. Whereas in the pruning algorithm, when the algorithm starts out, it says that I will initially make radius equal to infinity. But that initial infinity radius is the only reason is that it will allow me to slide down the very first path of this binary tree until I reach the leaf node. This part is easy. It doesn't take too many computations because I'm setting all of the S variables to be -1. And then I'm going to say that the metric that I get is going to be my R metric. So R became 7. Then I will go to the next one, and then now R became 4. As soon as R became 4, when I do the next iteration, I'm going to delete this subtree, because 5 is greater than 4. And so I'm able to kind of adaptively change the radius. So let us read the description of the pruning mechanism. So sphere decoding with pruning is that every time we reach a leaf node with metric m, we know that the solution to 4 must be contained in the sphere y tilde minus ls less than or equal to m. So basically we have to reach, first of all, a leaf node. We have to look at its metric, and then if our current radius is bigger than m, then we change radius and make it equal to m. Basically, we start out with radius which is infinity. It is the largest possible radius. And then we keep on reducing the radius. We keep on making the spheres smaller and smaller. And so our algorithm becomes smarter. So when we visit the leaf node 4, R is set to 4, which means that the algorithm will not follow branches from nodes that have branch larger than 4. And so it does not examine branches coming from 5. So that is the idea behind sphere decoding with pruning. This is this diagram here. There are other smart ways also. The symbols can be sorted in alphabetical order, or we can do some enumeration in some smarter ways, and so on. So that concludes our description of sphere decoding. Then there is the last algorithm, which is called, I think, finite complexity sphere or fixed complexity sphere decoder, which is actually not a sphere decoding at all, but it's a combination of brute force, and then subsequently, after brute force, we do simply the decision feedback. And so the main idea is that we do brute force up to certain level of the tree. Here they do brute force only up to r equal to 1. And then subsequent to that, they do the decision feedback. And basically, you will have here r is equal to 1. So there are 2 subtrees. And so you do decision feedback on both the subtrees. And so you will have 2 answers. And then you pick the one which is better. Here in this case, 5 is better than 8. And so you go with 5. So you still made an error. You didn't get to 4, which is the right answer. But well, that is because you did this enumeration only up to r equal to 1. If you did r equal to 2, now you will have 4 subtrees that you would do decision feedback on. And so now you will have 4 different answers at the output of decision feedback. 4, 5, 8, and 9. And then you will select the smallest one of them, which is 4. And so now you actually got the right answer. So finite complexity sphere decoding is actually a lot like the decision feedback interference cancellation, except that decision feedback is performed on multiple subtrees. How many subtrees? It depends on the R. If R is 1, then you will perform decision feedback only on 2 subtrees. If R is equal to 2, you perform decision feedback on 4 subtrees, and so on. So that is the idea behind the fixed complexity sphere decoding. The reason it is called fixed complexity is because your complexity is bounded here. You know that you are going to do brute force up to level R, so you know exactly how many computations you will need. And then subsequent to that, you are doing just the decision feedback. And again, that complexity is also fixed. A problem with the sphere decoding, even with pruning, is that the complexity may not be known ahead of time, although it will be definitely much simpler than doing brute force. The problem is that depending on H, the time the algorithm, meaning this sphere decoding algorithm, takes to finish, it will fluctuate. For some H, we may get lucky and the sphere decoding will be very quick because it kind of isolates the right subtree very efficiently. But you can probably imagine other cases where it may not be able to isolate the subtree very efficiently. For example, in this SD with pruning, instead of this metric lining up like this, if they had lined up exactly in the reverse manner, so first was 17, then 9, 8, 10, then you see that this pruning would not have helped much because 17 is so large, everything is below 17. So you didn't do much of pruning at all. Even 9 doesn't help you rule out any of these subtrees. 8 doesn't help you rule out. And so until you get to the leaf nodes which are like here, you may have to keep on visiting all of the leaf nodes, which can be computationally quite burdensome. Okay, so that is the summary of this paper. There are some other algorithms which are mentioned, lattice reduction, soft decisions, etc. We don't need to get into that. Semi-definite relaxation. Those are some other clever techniques. They are more I would say more narrow. I don't think that in the literature these techniques are getting as much attention. I think sphere decoding is probably one of the most popular algorithms. I'll put this paper on our classroom, and so you can read about this SDR detector or LR detection and so on. But the main algorithm that is described here is this figure 2. And this figure 2 already talks about 4 different algorithms that we saw. Okay, so that is all for today.